define acceleration. So what you'll write here is that it is the rate of change in velocity. Write rate of change in velocity per unit time. That is absolutely wrong. Whenever there is the concept of rate, it means that the time has been involved. So it's A is equal to V minus U over T. Do not write it as rate of change of velocity per unit time. That is wrong. It's simply like that. You can also write it like this, or you can write it, it's change in velocity per unit time. Part two is show that the maximum speed of the train is approximately 56 meter per second. So you see that it's given here as to 200 kilometers per hour. You need to convert it into meters per second. So basically, if you look very closely, it's 200 kilometers per hour, right? So what you have to do is you have to convert kilometers into meters and hours into seconds. So what you'll do is that you have here 200, you multiply it with 1000 to convert it to meters, and you need to convert 1 hour into seconds. So that would be 60. There are 60 minutes in 1 hour, and there are 60 seconds in 1 minute. So 60 into 60. So this is going to be what? This is going to be 200 into 1000 over 3600. The answer is approximately 55.5 is the answer, but the answer approximately is 56 meter per second. Part is calculate the time taken for the train to reach its maximum speed. So you should know that the formula is acceleration is equal to V minus U over T. And you know that it started all the way from rest. So the initial velocity is 0. The acceleration is 0.70. The final velocity is, since we calculated it earlier as 55.5, which was approximately 56 seconds. So U is what? U is 0 here. And we have T here, and this is going to be what? 55.5 over 0.70. It's going to be 79.2. And I can write here 79 seconds. The next part is the train has a total mass of 440,000 kilogram. Calculate the force which causes the acceleration of the train. So the formula is F is equal to ma, where F is the resultant force. The mass is 440,000 kilograms, and the acceleration is 0.70, right? And the value for the force is 310,000, right? Or you can also write here as 3.1 into 10 raised to power 5 Newton, right? The train travels into a headwind. The force of this headwind opposes the motion of the train. State and explain the effect of this force on the motion of the train. So the statement here is that it reduces acceleration because it opposes the motion of the train. It reduces acceleration, or you can also write here, it lowers the maximum velocity reached. And also the explanation here is that the force of the headwind uses the resultant force. It opposes the motion of the train. That's why what happens is that the force of headwind reduces. Moving on, a light dependent resistor, which is LDR, has a low resistance and high light intensity and a high resistance in the dark. Sketch a graph of resistance against light intensity for an LDR. So we have here on the y-axis, we have the resistance in ohms. For here, this is the resistance in ohm. And we have here the light intensity, right? So what you're going to do is you have to draw the graph, and you should know that for lower light intensity, the resistance is more, and for higher light intensity, the resistance is less. It's going to be a graph like this. At lower light intensity, we have a high resistance, and at high light intensity, we have a lower resistance. The next part is figure 5.1 shows the part of electric circuit used to turn on a light when it is dark. Uh, Complete the circuit in figure 5.1 with a symbol for a light dependent resistor LDR. What you're going to do is you're going to draw here the symbol for the LDR, and the symbol for the LDR is, the next part is explain why the lamp is off in the light, the lamp is on in the dark. Use ideas about potential difference in your answer. So they have laid emphasis here on the potential difference, right? You should know that the potential difference across LDR and potential difference across R is in same proportion as their values of resistance, right? This is the resistor, this is the LDR. What's going to happen is I'm going to write here the potential difference P dot B dot across and potential difference across R is in same proportion as their values of resistance. What it means here is that when there is more light, the resistance of LDR decreases, and the potential difference across LDR also decreases. And since the lamp is in parallel to the LDR, the potential difference across lamp will also decrease when there is more light. And when there is less light, the opposite is going to happen, right? So what's I'm going to write here that in light conditions, there is a smaller potential difference across LDR, right? And also there is a smaller potential difference across the lamp. So you know that if there is a smaller potential difference across the lamp, and you know that it's V is equal to IR, so what's going to happen is that since the resistance of the lamp is fixed, smaller V, then we have a smaller I. When there is a smaller I, the power dissipated by the lamp is less, right? Power is I square R. The power is less, right? So you can see that explain why the lamp is off in light and the lamp is on. So there is less power dissipated, and the lamp is, less bright. And what happens is that in dark conditions, happens is there is larger potential difference across LDR. And when there is larger potential difference across LDR, there is larger potential difference across the lamp. And when there is larger potential difference across the lamp, since the resistance of the lamp is constant, the current is going to be more, and there is more current, and hence it's more bright, and it's on, right? Okay, I'm going to write here the potential difference across the lamp same as potential difference across LDR. So we have used the concept of potential difference here. When there is more light, there is less resistance here, and there is less potential difference here across the LDR. When there is less potential difference across the LDR, there is less potential difference across the lamp. And when there is less potential difference across the lamp, what's going to happen is, since the resistance of the lamp is constant, there is less current, and the light, what's going to happen is the lamp is off because there's way less current. We have dark conditions. What's going to happen is that the resistance across the LDR is more. When the resistance is more, there is more potential difference, and there is more potential difference across the lamp. And when there is more potential difference across the lamp, there is more current, and hence it is on. The 6.1 shows an object O which is 5 centimeter away from the center of a thin converging lens capital L. The focal length of the lens is 3 centimeters. Figure 6.1 is drawn to full scale. So remember that whenever you have a full scale diagram, what you get it on the paper is that you can measure it with the ruler. So the distance that is from the center of this to the lens is 5 centimeters, right? The length is 3 centimeters. You can measure it exactly by using a ruler, right? It says this length is approximately, you see that this is 3 centimeters, right? We can measure it with the ruler exactly. So I call this, let's say I call this F. This is the focal point, and similarly, the focal point here would be at the same distance, right? 3 centimeters, and you use a ruler to measure it, right? Let's say this is also, you know, 3 centimeters. When you use a ruler, you'll get the exact measurements, right? So on figure 6.1, label the principal axis with a P. So this is the principal axis. I call this P. On figure 6.1, place a letter X at the focal point. So let's call this is the letter X that we have here, this one. This is also letter X. On figure 6.1, draw two rays from O to locate the tip of the image produced by the lens. So here you need to follow the rules. Rule number one is a line passing through the center of the lens will pass without any deviation, right? If I have a line that is passing through the center, it passes without any deviation. It's going to pass straight. You use a ruler for this, right? Make sure that you draw a straight line and you use a ruler for that. The second point is that the line should be parallel. The second to the principal axis, and then it's going to pass to the focal point. After converging through the lens, it's going to pass through the focal point, and you'll see that where these two lines will intersect, that would be where the image is produced. Right? The image is going to produce somewhere here. So in table 6.1, place a tick in the right-hand column next to all the terms that describe the image. So you can see here that the image is enlarged. It is of a bigger size compared to the object. Also, and you also need to draw the arrows here. Don't forget to draw the arrows, right? So this is where the image is formed, right? And also you can see that it's inverted and it's real. A real image is one which can be caught on a screen. So if you place a screen here, you can see this image clearly. Right? Moves closer to L, the new distance between L and the object is less than the focal length of L. Describe how the new image is different from the image in A4. What happens in this case is, let's say, I'm going to draw it here. Let's say this is the converging lens here. Let's say this is F. This point is F here. And let's say this is also F. And the object is somewhere here. You see, this is the optical center. So we follow the rules. A ray which is passing to the center is going to pass without any deviation straight. And the ray which is parallel to the principal axis, this is the principal axis, it's going to pass through F, right? And you see that these rays are diverging, right? And they cannot meet. So what you have to do is you have to extend them back, and they will extend back and they will meet somewhere here, right? And this is the image formed. And you see that this image is a virtual image, and a virtual image is one which cannot be caught on a screen. And you see that such sort of image is produced by using a magnifying glass, right? For magnifying glass, the object is placed before the focal length, as we have done it here. You can see that the image is, I'm going to write here, image is now virtual, as you can see, and it is upright, not inverted, it's upright, and also it is to the left of the lens, right? Previously, it was to the right of the lens, as you can see here. It is to the left of the lens. The image is to the left of the lens, or you can also write here, or behind the object. So the examiner is very fond of giving questions on magnifying glass, and you should know this, that the object is placed before f header.